this is the time to generalize the coherent states and produce the set of coherent states that are most useful eventually and most flexible. And we do them as follows. We basically are inspired by this formula. To write the following operator. And here we change notation. This x0 was here, but now we'll introduce what is called the alpha coherent state. Most general coherent state is going to be obtained by acting with a unitary operator on the vacuum. So far, so good. D of alpha, unitary. But now generalize what you had there. Here you put A minus A dagger minus A because that was anti-Hermitian. You put a real constant. Now this alpha will belong to the complex numbers. Quantum mechanics is all about complex numbers. You got like complex vector spaces, complex numbers. It's all over the place. So how do we do this? We do this exponential of alpha A dagger. And I want it to be anti-Hermitian. So I should put minus alpha star A on the vacuum. This thing for alpha equal this real number reduces to that. But now, with alpha complex, it's a little more complicated operator. And it's more general, but it's still unitary. And it preserves the norm. And it's most of what you want from these states. So the first thing you do to figure out what this operator does is to calculate something that maybe you would not expect it to be simple, but it's worth doing. What is A acting on the alpha state? Well, I would have to do A acting on this exponential of alpha A dagger minus alpha star A on the vacuum. Now, A kills the vacuum, so maybe you're accustomed already to the next step. I can replace that product by a commutator, because the other ordering is 0. So this is equal to the commutator, because the other term, when A is on the other side, is 0 anyway. And now I have to compute the commutator of A with an exponential. Again, it's a little scary, but A with an exponential e to the b, it's in the formula sheet, is Campbell-Baker-Hausdorff again, is AB e to the b if AB commutes with B. Well, this is A, this is B. A with B is, A with B, the exponent, is just alpha times 1, because it commutes. So it's a number, so this is safe. So you get alpha times the same exponential. But the same exponential means the state alpha. A little quick, isn't it? OK, A with B, this factor was alpha. And e to the b, anyway, on the vacuum is the state alpha. So there you go. You have achieved the impossible. you've diagonalized a non-Hermitian operator. This is not Hermitian, and you found its eigenvalues. How could that happen? Well, it can happen, but then all the theorems that you like about Hermitian operators don't hold. So it's a fluke. This can be done, but then states that correspond to different eigenvalues will not be orthogonal, and they will not form a complete set of states, and nothing will be quite as you may think it would be. But still, it's quite remarkable that this can be done. So this characterizes the coherent state in a nice way. They're eigenstates of the destruction operator, and they're the most general exponentials of creation and annihilation operators acting on the vacuum. Now, we knew that when alpha is real, it has to do with x0. So we've put a complex alpha. What will it do? A complex alpha, what it does is gives the original coherent state some momentum. Remember, the original state that we had was an x0, and how did it move? x0 cosine of omega t. So at time equals 0, it had 0 momentum. This creates a coherent state at x0, and it gives it a momentum controlled by the imaginary part of this thing. In fact, we can do this as follows. You can ask, what is the expectation value of x in this state? Well, x is written here, is d over square root of 2 alpha, a plus a dagger, alpha. And look, these are easy to compute. A gives on alpha gives you alpha. A dagger on alpha, you don't know what it is. But a dagger on bra alpha is alpha star. So this one you know on the right, this one you know on the left. And it gives you d over square root of 2 alpha plus alpha star. So it's square root of 2d real of alpha. So the real part of alpha is the expectation value of x. Similarly, so I'll go here. I'm almost done, waiting for the punchline. Similarly, you can calculate the imaginary or the expectation value of the momentum. Would be alpha, p, alpha, and p is a minus a dagger. So you're going to get alpha, alpha star minus alpha, so the imaginary part. So p is actually a square root of 2 h bar over d imaginary part of alpha. So the physics is clear. Maybe the formulas are a little messy, but when you have an alpha, the real part of alpha is telling you where you're positioning the coherent state. The imaginary part of alpha is telling what kick are you giving it to it. And you now have produced the most general coherent state. So how do we describe that geometrically? We imagine it the alpha plane. And here it is. The alpha plane, here is the vector, the complex number alpha that you've chosen, maybe for your state, some particular complex value alpha. On the x-axis, the real part of alpha is the expectation value of x over square root of 2d. The real part of alpha is the expectation value of x over square root of 2d. And the imaginary part of alpha is the expectation value of p over square root of 2h bar d. And there it is, your state at time equals 0. What is it going to do a little later? Well, that will be the last thing I want to calculate for you. It's a nice answer, and you should see it. It's going to take me 2 minutes. And what is it? Well, alpha at time t, you have to evolve the state, e to the minus I ht over h bar on the state, which is e to the alpha a dagger minus alpha star a, e to the, I'll put an e to the iht over h bar, and an e to the minus iht over h bar, and the vacuum. So I put a 1 here. I evolve with this, but I take the state and put this and that. This is simple. It's e to the minus IH omega over 2. That's the energy of the ground state. But what is this part? It's pretty much the Heisenberg operator, but the sign came out wrong. Well, it didn't come out wrong. It's what it is. It just means that what I have to put here is the Heisenberg operator at minus t, because I have t for minus t. So this is e to the alpha a Heisenberg at minus t dagger minus alpha star. I'm sorry, I have too many parentheses here. That's it, much better. Minus alpha star a Heisenberg of minus t acting on this thing. And what is this? Well, we have the formula for the Heisenberg states here. So you got e to the alpha. A dagger of minus t would be e to the minus I omega t a dagger. And here you have minus alpha star e to the I omega t a on e to the minus I omega h bar over 2 times the vacuum. And look what has happened. Alpha has become alpha times e to the minus I omega t, because the star is here. It's minus the star one. So the only thing that has changed is that this state, alpha at time t, is e to the minus I h bar omega over 2. I'm sorry, I'm missing a t here. Yeah, I drop, yeah, minus I omega t over 2 minus I omega t over 2 minus I omega t over 2 times the coherent state, the time-independent coherent state of value e to the minus I omega t alpha. That's the new complex number. That's what has happened. The number alpha has become e to the minus I omega t. Now, this is a phase for the whole state, multiplicative, it's irrelevant. So what has this alpha done? Has been rotated by e to the minus I omega t. So this, at the time t, is the state alpha t. Here is the state alpha, and it has rotated by omega t. So the coherent state can be visualized as a complex number in this complex plane whose real part is the expectation value of x at time equals 0, whose imaginary part is the expectation value of the momentum at time equals 0. And how does it evolve? This state just rotates with frequency omega all along and forever.